So hello, welcome to another CASIM video tutorial series on Arduino, Pure Data and Supercollider. Today's video is the conclusion of the recent tutorials on connecting a DIY Arduino and sensors to Supercollider to control a simple hybrid FM synth. In the previous videos we built a breadboard Arduino, two DIY force sensors and wrote a program in PD to receive the force sensor values from Arduino and control a synth. Today we're going to connect the Arduino to Supercollider to introduce a different audio DSP coding paradigm. And in this example we need to make a few simple changes to our Arduino code, and then I'll spend the bulk of this video describing how we get that data into Supercollider and parse it and map it to our synth engine. So have a look at the Arduino code. It's largely unchanged from the previous video. In our setup we set our pin modes. This is just really for the LEDs. It's largely unnecessary as far as Arduino to Supercollider goes. Then we take the average reading from each of the two pins, FSR1 and FSR2. We do some averaging, mapping and constraining to 8-bit range. Then we output those values to Pure Data, at least, using a combination of serial.print and serial.write. We serial print an ASCII value, then we serial.write the FSR reading, and then repeat for the second one. We serial.print a B ASCII code and then write the value. We could use that method in Supercollider, but it's a little more involved in parsing the data and converting it into human readable and human usable values, integers. So with a subtle and simple change, we can get the data into Supercollider and parse it, extract it, and use it. And the only change we made is that instead of serial.print and serial.write, I'm using serial.print for everything and terminating that packet of data with serial.println. I'll explain why later. The first thing we're printing is letter A and a colon, then our FSR value, then a colon, letter B, colon, and our second value. And that's all the sensors we're sending, all the values we're sending, so we terminate with println, which outputs a ASCII code 13 and 10. And in Supercollider, where I've built and described in previous videos a simple hybrid FM synth, we use the Arduino SMS external library to collect and parse that data. And I've an example here built already, or written already, but I'll write it from scratch and explain what I'm doing as we go on. So I'll close down that one. Here's my QFM synth. And again, just as a review, you'll recall that in simple FM synthesis, we have a sine oscillator whose frequency, center frequency, is modulated by a modulating oscillator. And the frequency of the modulating oscillator is the center frequency multiplied by ratio. And the amplitude of that modulator, which is not going directly to the output, it's going to the center frequency of the carrier. The amplitude is the center frequency multiplied by the ratio multiplied by an index. And then to make QFM, or quantized frequency modulation, we wrap that modulator in a latch, a triggered oscillator, and then we have a final oscillator to trigger that latch. And in the new synth def in Supercollider, all I've done really is just to tidy up the code a little bit. Instead of having that signal all on one line, UGens embedded within UGens, embedded within UGens, just for the sake of clarity. There are two ways to do this, and I'm demonstrating both of them here. But in this synth def, I'm using the clearer version. So I've created some local variables which represent the carrier oscillator, the modulating oscillator, and the triggering oscillator. And you'll see here that those expressions are the same as the previous version I'd used. Anyway, let's get on to the Arduino. So I'll make a new sketch or new patch. The first thing I'm going to do is access the native serial.port or serial port class. And if I query it by passing the method list devices and then shift enter to run that, I get a list of USB ports. Everybody's system will be slightly different, and mine's dev TTY USB 0. I'll copy dev TTY USB 0, paste it in here, and now Arduino SMS expects 2 arguments. The name of the port, well, I've just identified what that is. And the baud rate that I'm using, and you'll recall, is 38400. I don't want to have to type this out every time I'm accessing the Arduino Serial Bus, so I'll make a global variable with the tilde character and then just some name. I could call that foo, but we tend to use memorable and semi-descriptive names. So tilde ard, I've decided to call it Arduino SMS dev TTY USB 0 38400. And conceptually in Supercollider, what I want to do is take some action. I want Supercollider to respond to the incoming serial bus data. So I say ard.action equals, and I'm going to make a function, and this will run every time numbers, values, data comes in on the serial bus. How do we access that data? If I make an argument and call it foo for the time being, and then say foo.postln, what this function does is .action accesses all the data that's coming in on the serial bus, and I can post that data to the debug window at the bottom here. So I can simply just run that. There we go. Say the information that I have asked the Arduino to send, A colon, then value, colon B colon, then the second value. That's all coming in. We can see in the post window here, A colon, changing value, colon B colon, the second value. How do I parse that data? It's quite simple. Let's clarify things here. So instead of foo, I'll say message.postline. That'll run the same, so I don't need that post line. I'm going to make a local variable and call it list. Var list. What is list? The list is going to be that packet of data, the message, and I'm going to dot split at a string or symbol. Well, what string or symbol am I using as a delimiter? I'm using the colon. If I say list.postln, look at how the values change in the post window, or the format changes. I now have an array of those 4 values, or that four pieces of information. I have the A, the first value, and a B, and the second value. What it effectively does is it strips out the delimiter that I put in, the colon. So now we have an array. The first item is what? Well, it's indexed at 0 because we index items in an array starting at 0. If I say list 0th item, there. Well, it's just an A. I can try changing values, but I'm not seeing anything. List 1 is the value of the first sensor. There's the third item in the array. That's just a B. The fourth item in the array is the second sensor. So I could say print out an array consisting of the first item and the third item. It should work. There we go, we have an array of 2 values. So how do I grab them individually? Well, that should be clear, shouldn't it? Let's make 2 more variables. Call the first one val1, the second one val2. Val1 is my array of values, and it's the second item in the list. We'll say .postln. Just copy that. Value 2 is the 1, 2, 3 is the last item in the array. Run that. There's value 1. There's value 2. I've got them now. I encountered a major problem the last time I tried this. As a test run, my operating system froze, Supercollider froze, wouldn't crash, wouldn't Control-Alt-Delete or anything. My entire system freaked out. And the reason is because I forgot this method as integer. Somewhere down the line, maybe on the USB bus, maybe on the Open Sound Control communication between Supercollider IDE and the synth engine, the sound server, something was getting garbled and the entire system broke down. And the solution is to ensure that value 1 is only ever a number. And now I can say, let me see, LinuxP, let's use the first value as our center frequency control. I'm going to use the first value as my center frequency control. And the incoming range is 0 to 255, and I want that to output between 50, and I know that anything in this mapping beyond 1000 or 2 kilohertz creates white noise. And because it's a frequency value, that's why I'm mapping linear input onto exponential output. I'll copy and paste that. .postln as well. Control copy, verify, just change as we need. Value 2 is list item number 4 as integer, and we're going to map. Yes, we'll use Linux 0255, and we will say between 0.1. We can't say 0 there because we are getting exponential output. We don't want divide by 0 or not a number, so this third item in the mapping, minimum of the output can't be 0. And I'll just say 10 here, because I know what's expected by my synth. Run that. Now, there's my trigger ratio between 0 and 10. And here's my center frequency between 50 and 1000. Don't need to post ln. I'm going to start my sound server, synth server. Add my synth. initialize it. And the dynamic values that I'm inputting to this synth, certainly from 2 FSRs, are the center frequency and the trigger rate. So that's \CF and \TR. Let me just turn that down. So remember, Arduino SMS.action is going to react. It's going to execute this function every time values come in. So I will say, what's the name of my synth? I decided to call it tilde for a global variable QFM.set \center frequency. Well, that's going to be value 1 now that I've remapped it. Then QFM.set trigger rate, that's going to be value 2. Run that, and we shall listen while I mess with the FSRs. That's just the center frequency. This is just the trigger rate. And I've set it up purposely like that. Activating one FSR has no great radical effect. We have to use both of them at the same time. Nice. So I skimmed over, or went through the Supercollider side of things fairly quickly. That's because this isn't a Supercollider tutorial. Just copy the text off this video, or copy the code off this video if you want. I will be doing some slightly more in-depth Supercollider tutorials, but for the time being, for the foreseeable future anyway, I want to focus on physical hardware interfaces, DIY sensors. And I used pure data in Supercollider purely as an example of how we can get DIY sensor data into sound synthesis engines.